Under the hot African sun, a convoy of trucks arrives at a platinum mine, carrying the disassembled parts of a hydraulic excavator that will soon weigh 500 tons. The anticipation of seeing such a machine take form is undeniable. The landscape itself seems to wait, as if aware something extraordinary is about to rise. The assembly begins with the slewing ring. Its surfaces must be perfectly clean and dry before adhesive is applied. A 120-ton crane then lowers the ring onto the undercarriage, where bolts are tightened first by hand and then by hydraulic wrench. The middle section of the undercarriage is joined to one of the track carriers. It is supported with jacks, while the second track carrier, weighing 35 tons, is positioned beneath and bolted securely. Each connection feels like another step toward awakening the giant. With both tracks in place, a bulldozer aligns the pads, each weighing nearly a ton. Lubricant and heavy-duty grease are applied to the slewing gears. Two cranes now lift the massive superstructure frame onto the ring, guided into place with dowel pins before bolts are torqued and marked. The teamwork between cranes and crew shows remarkable coordination. Even small adjustments require complete focus, as the sheer size leaves no room for error. Next come the boom cylinders, mounted with lubricated pins. The 37-ton motor module is then set down with laser alignment accurate to hundredths of a millimeter. The cab module, including its switchgear, follows. Before the boom is lifted, stick cylinders and hydraulic hoses are prepared. Two cranes carefully position the 50-ton boom, while a wheel loader drives in the giant pin. The sight of metal connecting metal in perfect sequence is thrilling. At greater heights, mobile platforms assist workers in mounting cylinders and other components. The cooler module, weighing over 7 tons, is installed, followed by the heaviest single part, the 60-ton counterweight. It is lowered slowly into place with bolts tightened by torque multipliers. Railings, walkways, and service equipment are then added, completing the superstructure. By now, the excavator begins to resemble its final powerful form. Attention turns to the stick and bucket system. Pins sprayed with lubricant are driven in, and 2 bucket cylinders are mounted. Electricians and mechanics spend days connecting hydraulic and electrical lifelines, ensuring safety and performance. Fluids are filled, grease applied, and systems inspected. Every completed line and tightened bolt adds to the sense of readiness. The excavator is moved toward its working position, where a 25 cubic meter bucket is mounted. With final cylinders in place, the RH200E is ready for operation. The first scoop into tightly packed rock feels like a triumph of human engineering. Trucks of 150 tons line up, and loading begins without delay. The power on display is immense, yet entirely purposeful.
Massive machinery lines up at the edge of the Peruvian desert, ready to tackle Minajusta's toughest challenges. A new era is unfolding at Minajusta, Peru, as more than 50 pieces of Cat machinery arrive on site. The highlight is a fleet of 26 massive CAT 793D trucks, each able to haul 250 tons. This incredible scale marks the start of a powerful chapter in Peruvian mining. Laying new train tracks is an impressive display of modern engineering. Specialized flat cars carry long welded rails, stacked for efficiency and minimal joints. At the job site, hydraulic rail handling machines extend and smoothly lower each steel rail onto the prepared bed. Standard rail lengths often reach 120 meters, reducing the number of fish plates and enhancing ride comfort. Workers use alignment tools to ensure every rail is perfectly straight before fastening. Ballast is distributed beneath and around the structure for drainage and support. GPS-guided survey equipment checks track geometry for compliance with national standards. Powerful tamping machines compact the ballast and lock rails and sleepers in place. Installation rates can exceed 1,500 meters of track per shift with this method. The finished track is inspected thoroughly before trains can run. The Leehair LG1750 mobile crane dominates the wind farm construction site with its immense lifting power and reach. This giant machine is tasked with handling the heaviest components, including long turbine tower sections and massive blades. With a maximum lifting capacity of 750 tons, the LG1750 uses a lattice boom system that can extend up to 140 meters, making it ideal for tall wind turbine installations. The crane is supported by a multi-axle wheeled chassis, distributing weight evenly on soft ground. Its hydraulic outriggers are deployed and precisely leveled, creating a stable base before any lift begins. The boom sections are connected using heavy-duty pins and hydraulic tools to ensure structural integrity during operation. On-site, rigging crews attach high-capacity slings and lifting beams to the turbine segments, coordinating closely with the crane operator. Wind speed sensors and redundant safety systems are always active, automatically suspending operations if limits are exceeded. During a lift, the crane's load moment indicator constantly monitors torque, ensuring the crane operates within its rated limits. For wind farm projects, LG1750 can lift nacelles, weighing over 100 tons to heights above 100 meters in a single operation. Once a lift is complete, the crew prepares the crane for the next heavy load, maximizing efficiency and safety on every project.
How can a scrap car be crushed at a junkyard? At vehicle dismantling yards, old cars are first stripped of valuable parts like engines, transmissions, and tires. The remaining body is then positioned under the car crusher. Hydraulic presses apply immense force, compressing the entire vehicle into a flattened, mangled mass. Absolutely crazy how fast an entire car can be obliterated. The crushed vehicle is then ready to be transported to steel mills, making recycling more effective and sustainable. Car crushers have become essential tools in the dismantling industry, allowing operators to process vehicles quickly while recovering maximum material. The way old cars are turned into reusable metal is surprisingly satisfying. Each step emphasizes efficiency, safety, and industrial resourcefulness.
Bringing the Leehur R9800 mining excavator to Australia is an impressive demonstration of careful planning and flawless teamwork. The process begins at the production site in Colmar, France, where the excavator is divided into several massive modules. Each part is carefully secured and loaded onto a cargo ship for its long ocean voyage. After weeks at sea, the ship docks in Australia. The modules are unloaded and transferred to heavy transporters for a demanding 272-kilometer journey by road to the Moolarbin coal mine. The team must navigate winding rural roads and contend with unpredictable weather. Wind gusts reaching 70 kilometers per hour sometimes force the entire operation to pause for safety reasons. At the mine site, cranes and crews get to work. Each module is lifted and assembled one by one, gradually forming the completed R9800. Every connection point is inspected closely as the modules are joined, making sure all systems align perfectly. Hydraulic, electrical, and mechanical systems are connected and tested, with every step carefully checked. Once assembly is finished, the excavator is displayed during an open day, giving the local community a chance to see this engineering marvel up close. After final checks and adjustments, the R9800 is ready for full mining operations. Watching this journey highlights the dedication, precision, and logistics behind every successful mega project. Bringing the Leehur R9800 mining excavator to Australia is an impressive demonstration of careful planning and flawless teamwork. The process begins at the production site in Colmar, France, where the excavator is divided into several massive modules. Each part is carefully secured and loaded onto a cargo ship for its long ocean voyage. After weeks at sea, the ship docks in Australia. The modules are unloaded and transferred to heavy transporters for a demanding 272-kilometer journey by road to the Moolarbin coal mine. The team must navigate winding rural roads and contend with unpredictable weather. Wind gusts reaching 70 kilometers per hour sometimes force the entire operation to pause for safety reasons. At the mine site, cranes and crews get to work. Each module is lifted and assembled one by one, gradually forming the completed R9800. Every connection point is inspected closely as the modules are joined, making sure all systems align perfectly. Hydraulic, electrical, and mechanical systems are connected and tested, with every step carefully checked. Once assembly is finished, the excavator is displayed during an open day, giving the local community a chance to see this engineering marvel up close. After final checks and adjustments, the R9800 is ready for full mining operations. Watching this journey highlights the dedication, precision, and logistics behind every successful mega project. High-stakes mining operations are redefining what's possible beneath the Earth's surface, and few machines command attention like the Wirtgen surface miner. Mining starts with robust cutting drums, slicing through limestone, bauxite, or coal. No drilling or blasting required. Operators expertly steer these giants, cutting precise benches, while integrated drainage ensures dry material extraction. The elimination of explosives means lower noise and dust emissions, even near infrastructure. It's impressive how a single surface miner can handle both extraction and loading, reaching outputs over 3 million tons of bauxite per year in Guinea. Material is windrowed alongside the machine, allowing selective loading and streamlined quality control. Stable, truck-friendly haul roads are built directly by these machines, boosting transport efficiency and cutting logistics costs. Specialized belt conveyors transfer crushed ore straight onto dump trucks, keeping production continuous day and night. I can't help but marvel at the sheer productivity. 3 key processes combined into one seamless workflow. The surface miner's rugged mechanical belt drive delivers full power to the cutting drum, even in tough conditions like Australia's coal mines. Mines benefit from precise control, safer operations, and optimal resource use with this approach. Harsco manages steel slag from furnace to recycling. Specialized carriers transport hot slag pots to pits for cooling and safe handling. Powerful magnets recover valuable metal from cooled slag. Processed slag is then recycled as road base or fertilizer, maximizing resource recovery and minimizing waste. At Cologne/Bonn Airport, renovating the 3,815-meter-long runway is a feat of logistics and precision. Asphalt is milled and replaced section by section over weekends, using 8 pavers, 28 rollers, and over 180 trucks. Basalt aggregate ensures durability against frost and heavy traffic. Continuous lab testing guarantees quality. Each stage is tightly coordinated, keeping the airport operational while delivering a flawless new runway surface.
Transforming an entire bus into reusable materials is not a simple task. It's a carefully orchestrated operation where mechanical power meets precise control. Every movement of the crane and claw is calculated to ensure safety, efficiency, and maximum material recovery. The enormity of the bus contrasts with the subtle adjustments required by operators, revealing the expertise behind industrial recycling. Special attention is given to the sequence of impacts to minimize stress on the crane itself. NA crane hoists the vehicle carefully, ensuring stability before any contact with the heavy claw. Operators check alignment from multiple angles, aware that even a slight imbalance could compromise safety or efficiency. The bus is then subjected to repeated impacts from the claw, each strike methodically planned to break the structure into large, manageable sections. Panels, roofs, and engine components gradually separate, illustrating the combined power of mechanical force and human oversight. Secondary crews prepare adjacent zones to handle fragments safely, preventing bottlenecks in the workflow, and every strike is measured. Operators adjust the claw's height, angle, and grip, making minute changes to account for the bus's shifting weight. As pieces fall away, they are immediately collected or directed toward sorting areas. The engine, transmissions, and other heavy assemblies split under the controlled blows, while lighter elements, such as plastic panels, seats, and glass, fragment into smaller pieces for downstream separation. Unexpected bending or twisting is quickly countered with small adjustments to the claw's approach, and workers continuously monitor the crane's hydraulic pressure to prevent overload. The hydraulic pressure of the crane is fine-tuned continuously to adapt to the bus's changing weight distribution. Occasionally, stubborn sections require precise adjustments, guiding the claw for targeted strikes. Small debris is swept away between strikes to maintain a clear operational zone. The repetition of strikes reveals an almost hypnotic rhythm, each blow contributing to a gradual yet dramatic transformation. Workers maintain constant vigilance, observing how the bus flexes, cracks, and splits under the pressure. Adjustments are often required mid-process, as the vehicle can shift unpredictably during heavy impacts. Engine blocks are disassembled piece by piece under controlled claw pressure. The workflow demonstrates how mechanical engineering and human planning intertwine, creating a system where even complex, irregular shapes like a bus are reduced efficiently. Communication between operators and ground staff is constant, allowing quick responses to any unexpected shifts. NTHE final stages involve repeated pounding to ensure all sections are within manageable dimensions. Every remaining heavy component is addressed individually, while smaller fragments are funneled into conveyors for further separation. The cumulative effect of dozens of controlled strikes results in a compact, organized pile of recyclable materials. Observing the entire sequence from positioning to complete fragmentation underscores the interplay of power, precision, and human expertise. This methodical approach not only maximizes material recovery, but also ensures safety and operational consistency. Even after the bus is shredded, crews inspect the site to ensure no hidden hazards remain. NTHE's spectacle of a bus being dismantled in such a systematic way is fascinating. It illustrates how large-scale recycling facilities manage complex machinery, transform unwieldy objects, and extract value from what might otherwise be discarded. Each moment reflects careful planning, rigorous attention to detail, and the seamless integration of advanced equipment with human judgment. The repeated strikes of the crane claw are not random. They are a choreographed series of actions that gradually convert the enormous vehicle into usable components. Watching this, one gains a new appreciation for the engineering, strategy, and labor behind industrial shredding. The Meripede OJK 1.3 auger ditcher cuts through peatland with unmatched efficiency and control. Mounted on a 200 horsepower farm tractor, this machine cuts through peatland obstacles with a single pass. Each rotation of the auger slices through roots, stumps, and small trees, making ditch formation seamless. Operators guide the tractor along the designated strip, ensuring the ditch reaches maximum depth in one movement. Peat is flung evenly across the strip, preventing uneven accumulation and maintaining soil balance. Even when frost hardens the ground, the screw ditcher continues to perform without interruption.
Power on the field takes a different form when a track tractor connects to a massive plowing system. The Case Quad-Track, shown here, combines tracked mobility with a multi-blade plow, reshaping soil in wide passes. The first impression is the sheer stability of its tracked undercarriage. Operation begins with the engine, delivering high torque suited for pulling heavy implements. Diesel output is channeled into a transmission designed for continuous load, keeping traction constant. The track system distributes weight over a larger surface, minimizing soil compaction. It feels as if the machine glides even while hauling immense equipment. At the next stage comes attachment. A reinforced hitch links tractor and plow frame. Hydraulic connections bring the plow into position, raising or lowering sections as needed. Multiple blades align in sequence, each positioned to cut and turn soil efficiently. The coordination between tractor and plow is striking to watch. There's a sense of harmony as machine and soil interact in perfect rhythm. As the tractor moves forward, the blades slice into the ground. Each one lifts a section of soil, flipping it aside to expose fresh layers. Following behind, additional rollers and discs break clods and smooth the surface. The transformation of the field is dramatic in just one pass. Hydraulics manage adjustments on the go. Operators control depth and angle from the cab, ensuring consistent plowing despite variations in terrain. The robust track system maintains stability, preventing slippage on soft or uneven ground. Every motion shows how design supports both power and precision. Even at a distance, the scale of movement captures attention instantly. Finally, the plowing run leaves behind parallel rows of overturned soil, ready for planting. The system demonstrates not only strength but efficiency, reducing time compared to traditional equipment. On California Highway 25, road building unfolds with striking coordination of machines. The Vogel AMT3000-2i material feeder delivers asphalt steadily to the Vision 5200-2i paver, which works with the VR600 screed. The rumble of engines instantly conveys the scale of the task. The process begins as trucks unload asphalt into the hopper of the feeder. Its conveyor belts carry the hot mix without interruption, preventing segregation of material. Each transfer feels like a pulse, keeping the project alive. Next, the feeder channels asphalt directly into the paver. The paver spreads material evenly ahead of the screed, which compresses and levels it. Sensors help maintain consistent thickness across the lane. Tiny adjustments in the screed ensure smooth transitions. Operators remain attentive, coordinating speeds between feeder and paver. Their work minimizes delays and maintains continuous paving. The steady pace creates a rhythm that defines efficient construction. Trucks rotate in sequence to keep the feeder supplied, avoiding idle moments. Finally, the newly laid surface shows uniform compaction and texture, ready for traffic after curing. The transformation of rough ground into smooth pavement feels immensely satisfying. Road building here is a demonstration of machinery and human skill working as one. Strength in design becomes clear when watching a tractor face an urban obstacle. Instead of a field, the challenge here is a tall curb, testing the way power, wheels and hydraulics combine. The moment the machine tilts upward, tension fills the scene. The process begins with its diesel engine, supplying steady torque to the gearbox. Low-end force gives traction, essential when lifting heavy wheels onto an incline. Multiple gear ranges allow smooth power delivery on mixed terrain. Every sound of the engine feels purposeful. The first maneuver is unique. Both large rear wheels roll forward into the middle position, acting as a base. This pivot supports the front, allowing the two front wheels to rise and mount the curb. At this point, the auxiliary middle wheels remain steady, locking the structure. Viewers can sense the clever mechanics at play. Once the front wheels climb, the sequence changes. The smaller middle wheels move slightly back, releasing the load they carried. Freed from acting as the pivot, they roll to the rear while the tractor shifts balance. The transition is surprisingly smooth for such a heavy vehicle. Now the rear axle takes control. Its reinforced build distributes power equally, driving the large rear wheels up and over the curb. Together with hydraulic assist in steering, the tractor maintains stability until all four main wheels are firmly above the obstacle. Each push forward seems to underline reliability. Safety elements remain visible throughout. A rollover protection frame surrounds the operator, and the compact body allows movement in confined roadsides. Testing like this highlights engineering discipline more than advertising claims. In the final moment, the Erkant tractor stands fully on the higher surface. Engine, drivetrain, hydraulics and axle design prove themselves in unison. The climb ends with an impression of durability and confidence.
In the mountains of Artvin, the Yusufeli Dam rises as an extraordinary symbol of engineering ambition. Planned as one of the tallest double-curvature concrete arch dams in the world, it will stand 275 meters high once completed, ranking second globally in its category. The scale of such a project makes each stage of construction feel both monumental and intense. Its power station, designed with a 540 megawatts capacity, will generate 1.8 billion kilowatt-hours annually, enough to supply electricity to 750,000 people. Imagining the daily life of workers here brings a sense of awe at human perseverance. The process begins with the preparation of the riverbed and the stabilization of the surrounding cliffs. Blasting and excavation remove huge quantities of rock to carve a foundation capable of withstanding the massive water pressure. Layers of support are added to ensure no weakness remains. Specialized concrete batches are produced and transported to the site in constant rhythm. This concrete is designed to handle both compressive forces and the thermal stress of curing in massive pours. Placement of the dam body advances section by section. Concrete is poured in blocks, each carefully aligned to lock into the next. The arch shape is calculated to transfer water pressure directly into the bedrock of the valley. Cooling pipes embedded in the concrete circulate water to regulate temperature and prevent cracking. The sheer coordination between teams at this stage feels almost like an orchestra of engineering. Parallel to dam construction, the diversion tunnels are prepared to manage river flow. Water is rerouted through these channels to allow dry conditions for building. Once completed, steel gates control when the river returns to the reservoir basin. Powerhouse caverns are excavated deep inside the mountain, housing turbines and generators that will eventually convert water energy into electricity. Inside these chambers, the scale of the machines dwarfs the people working beside them. Installation crews assemble penstocks, massive pipes designed to guide pressurized water into turbines at controlled speeds. As the project nears completion, attention shifts to finishing works, sealing joints, testing mechanical systems, and preparing for reservoir filling. When the water rises behind the arch, it will create a vast lake stretching through the valley. The thought of mountains giving way to a man-made sea evokes both wonder and gravity. The Yusufeli Dam stands not only as infrastructure, but as a landmark of determination, technology, and collective labor, transforming the flow of the Peru River into a sustainable source of power.
The scale of energy production becomes clear when observing a fracking operation in action. At the White Wolf Well in the Permian Basin, the process unfolds with engineering and power working hand in hand. The first glance already suggests that this is no ordinary construction site, but a system built to draw hidden energy from the earth. Operations begin with the wellhead, where drilling has already reached deep shale layers. High-pressure pumps line the surface, prepared to push fluid mixtures into the wellbore. These mixtures, often made of water, sand, and chemical additives, are essential to open tiny fractures within the rock. The sheer intensity of the pumps creates an atmosphere that feels charged with unstoppable force. Once pumping begins, the fluid carries sand into the fractures. This sand acts as a propellant, keeping the cracks open so oil and gas can flow freely. The sight of lines, valves, and manifolds arranged in sequence shows how coordination keeps the system balanced. Each valve turn represents a point of control over enormous underground pressures. It almost feels like every small adjustment has the weight of the earth behind it. Next comes monitoring. Operators track pressure gauges, flow meters, and digital readouts to confirm stability during the fracking stage. Trucks and storage tanks remain nearby, supplying water and collecting recovered fluids. Finally, as pressure cycles are completed, the flowback stage begins. Fluids return to the surface, separating into water, gas, and oil. Recovery equipment directs these resources into containment systems for further processing. By the end, the well stands ready to contribute to energy supply, the ground beneath transformed into a channel of production. The closing view of the site gives a sense of both exhaustion and achievement,